In the last class, we derived a very important result in information theory, which states that the average length of a code can never be greater than the entropy of a source. So, what we derived was average length has to be always greater than or equal to the entropy of the source measured in array units. Now, to appreciate the importance of this result, let us revisit some of the examples which we had studied earlier in our course. So, one example which we had considered was that we had a source S consisting of 4 symbols S1, S2, S3, S4, each with each of these symbols are equiprobable. So, we know that the entropy of this source measured with the base 2 is equal to 2 bits per symbol. Now, if I try to design any code, a binary instantaneous code, then my length of that code can never be less than 2 bits per symbol. And in this case, each of these probabilities Pi, which is equal to 1 by 4, is of the form half raised to 2. So, what it implies that I can design a compact code with 4 code words each of length 2, and one such code is so. Now, the length of this code is also 2 minutes per symbol. So, there exists no uniquely decodable code for this source with smaller average code word length, that is the length of 2 minutes per symbol. Now, let us look at one more example to understand the derivation of that important result, that is L is greater than or equal to entropy of a source. So, if I take this same source S with the same 4 symbols, but with different probabilities given as half, 1/4, 1/8, 1/8, then the entropy for this source will turn out to be 1/3/4 bits per symbol. Earlier in our course, we had designed an instantaneous code for this source, and that code was given as S1 is 10, S2 is 110, S3 is 1110, and S4 is 0. This code is uniquely decodable code. In fact, it is a instantaneous code. Now, if you calculate the length for this code, it will turn out to be equal to 1078 minutes per symbol. So, even in this case, we find that the length of the code is greater than the entropy of the source. But now, each Pi in this case also is of the form Pi is of the form half raised to alpha I, where alpha I belongs to integer. Therefore, it is possible to achieve the lower bound of 134 bits per symbol, and this is done by setting li's equal to 1, 2, 3 and 3 respectively for this 4 symbol S1, S2, S3 and S4. So, the code would be S1 0, S2 10, S3 110 and S4 111. If the length, the average length for this code will come out to be 134 bits per symbol. So, again in this case we find that the length, average length turns out to be equal to the entropy of the source. And as a final example, to explain the importance of L is equal to Hs, let us consider a source S with 7 symbols as, so I have a source S consisting of 7 symbols S1, S2, S3, S4, S5, S6, S7, each with symbol probability is given as 1/3, 1/3, 1/9, 1/9, 1/7. Now, the entropy for this source we will take in the 3 array units. If you calculate, that will turn out to be 13/9 trinary units per symbol, and again we find that the symbol probabilities are of the form 1/3 alpha I, where alpha I belongs to integer, and we can, once we have the lengths, alpha i's are nothing but the lengths for the code, and we can design the instantaneous code as follows. S1 is 0, S2 1, now, if you calculate the length for this code as pi li I is equal to 1 to 7, it will turn out to be 13/9 trinary symbols per source symbol. So far what we have seen is that we have looked at the coding problem for the 0 memory source with symbol probabilities of the form 1/r alpha I. So, if I have log r 1/pi is equal to Li, if I have my pi's of this form, then I can write log r 1/pi is equal to Li, where I choose my Li's equal to alpha I. Now, the next question arises is that if this condition is not satisfied, then how do I choose my length? Now, what it means that if log of r 1/pi is not an integer, then how do I choose my lengths? It might seem reasonable that a compact code could be formed by choosing Li as the first integer which is greater than log r 1 by pi. Now, this tempting conjecture is not valid. If we select Li's in this manner, it is not necessary that we will get a compact code, but selecting Li's in this manner where Li's is the integer which is just larger than log r 1 by pi can lead to some important results. So, let us select Li therefore as the unique integer satisfying this condition. So, what we will do is we will select Li's as an integer which is just larger than this value. It means that it follows this inequality. So, if I choose a set of Li's which follows this inequality, then the next question is it possible for me to design or synthesize an instantaneous code which uses this set of Li's? So, that question can be answered. That question can be answered if I can test the Kraft inequality. So, taking exponential of the left inequality of equation 1, we will get 1 by pi is less than or equal to r of Li, which implies that pi is greater than r minus Li. Now, summing 2 over all i's, we obtain, if I sum this over all i's, assuming that the source is of size q, then I can write this relationship, and this is 1, therefore, I get this relationship. Now, this relationship is, you know that we have discussed this earlier, and we have shown that if this condition is satisfied, then it is possible for us to get an instantaneous code for that source. So, this choosing Li's according to this relationship given by 1 is acceptable for synthesis of instantaneous code. Now, equation 1 defines an acceptable set of Li's for an instantaneous code. Multiplying equation 1 by pi and summing up over all I, we will find, if I sum this up, pi summation log r 1 by pi, I is equal to, pi log r 1 by pi to pi Li pi log r 1 pi plus pi. These are summed over all i's. We get the relationship as this is the entropy of the source measured in RA units this is the average length of the code another very important result which we have derived. Now, there is a difference between this result and the result which we saw earlier. Another result which we saw earlier was HRS is less than or equal to L. There is an important difference between this relationship and this relationship. This relationship expresses a bound for the average length of a code independent of any particular coding scheme. The bound requires only that the code be instantaneous, whereas equation 3 on the other hand is derived by assuming the coding method given by equation 1. So, if I use the coding method described by equation 1, then I get this relationship, and this relationship provides both a lower and upper bound on the average length of the code. Now, since this relationship is valid for any 0 memory source, we may apply it to the nth extension of the source. Let us see basically what happens if I apply this kind of coding scheme to an nth extension of a source. So, let us assume that I have a source S which is a 0 memory source, and I look at its nth extension of this source. If I follow the strategy for coding which is given by this equation, then this equation is also valid for the nth extension, because nth extension of a 0 memory source is again a 0 memory source. So, the relationship which I will get is HR Sn is less than equal to Ln less than equal to HR Sn plus 1. Where Ln is the average length which is defined as probability of sigma I lambda I is equal to 1 to where q is the size of the source, q raised to n is the size of the nth extension of the source, sigma i's are the symbols of the nth extension of the source Sn, lambda i's are the length. So, lambda I corresponds to the length of the code word corresponding to symbols from nth extension, that is sigma I. This is the average length, and ln by n will give me the average length for code symbols used per single source symbol from S. Now, we have also seen that HR Sn, that is the entropy of the nth extension of a 0 memory source, is equal to n times the entropy of the original source. So, based on this relationship, we can write this equation as what this equation says is that it is possible to make ln by n as close as we wish to HRS by coding the nth extension of S rather than original source, that is S. So, because as n keeps on increasing, 1 by n will tend towards 0. So, in that case ln by n will tend towards HRS, that is the entropy of the original source. Now, so limit of n tending to infinity would be ln n is equal to HRS. This is a very important relationship which we have derived. This equation is known as Shannon's first theorem or the noiseless coding theorem. It is one of the two major theorems of information theory. Equation phi a tells us that we can make the average number of R-array code symbols per source symbol as small as possible, but not smaller than the entropy of the source measured in R-array units. So, the price which we pay for decreasing ln by n quantity is the increasing complexity of the coding scheme. Now, all this discussion which we have done pertains to a zero memory source and its extension. The next question arises is, are these results also valid for a source which is not a zero memory source, but say a Markov source. So, let us extend our discussion to a Markov source. Let me assume that I have a Markov source S and I have its adjoint S bar. We have seen the definition of an adjoint of a Markov source. Adjoint of a Markov source is a source with the same source symbols as the source alphabet as the source S, and the symbol probabilities of the symbols in S bar is the same as the first order symbol probabilities of source S. So, that is the definition of S bar. Now, the process of encoding the symbols in the source S and the symbols which are identical to the source in the source alphabet S into an instantaneous block code is identical, because the source symbols are same and the probability of the symbols are also the same. In that case, what it means that the average length, which is defined as Pi Li I is equal to 1 to q, this average length is also identical for both S and S bar. S bar, however, is a zero memory source, and we may apply the earlier derived result to obtain HR S bar is less than or equal to L. Now, we also have seen that entropy of the original source is always less than or equal to the entropy of its adjoint, and this is less than or equal to L. So, what follows is that HRS is less than or equal to L. So, again even for a Markov source we have shown that the average length of a code when we code the symbols individually in the source is greater than or equal to the entropy of the source. Let us extend this result to an nth extension of a Markov source. So, I have a source S which is a Markov source, and I am looking at the coding of this source in groups of n elements. So, that means I am looking at Sn where I code Si1, Si2, Si3 up to Sin as one unit. Now, if I start coding the source original source S in blocks of n source symbols, then I can say that this source symbols form a new source symbol which is Vi, and now I will range from 1 to q raised to n. Now, let us follow the same strategy which we followed earlier for a 0 memory source. Now, for a 0 memory source and its nth extension, we had derived a result saying that ln is greater than or equal to this. This is a result which we had derived for the 0 memory source and its nth extension. Now, based on this, same thing is valid for a Markov source. I can say that ln is greater than or equal to h of v less than h of v plus 1. So, the same result is valid when I code this source in groups of n source symbols. Now, we have also seen that by definition HV is equal to n times HNS, where HNS is the average information per symbol. So, if we go by this definition which we had seen earlier in our lectures, I can write this expression as n HNS greater than or equal to ln Now, if I divide both the sides by n, what I get is this result. Now, this is the average length of code symbols per source symbol of S. Now, if I take the limit as n tends to infinity, I will get limit n tending to infinity ln by n is equal to h infinity s, and this is the entropy of a source, which is a Markov source. So, again we have derived the result that if I want my average length to be as close as possible to the entropy of the source, then I have to use the extensions of the source. Now, another parameter we can define which relates the entropy and the average length of the source, and that is known as efficiency of a code. Efficiency of a code is defined as entropy of a source divided by the average length of the code for that source. So, this is by definition an efficiency of a code. What is desired is to have as large as possible the value for this eta. Now, a question that arises is that we have used the coding technique which is based on this inequality. So, this inequality provides us a method of choosing the word lengths Li. By encoding the symbols from Sn and taking n sufficiently large, the quantity ln by n can be made as small as possible, but it cannot be smaller than the entropy of the source. The question is, suppose if n is not very large, n or capital N, if this quantity is not very large, the theorem does not tell us what value of L, that is the average length, we shall obtain in that case. It does not guarantee that L or ln by n will be smallest for that fixed n. Let us try to understand this with a simple illustration. Suppose I have a source consisting of 3 symbols S1, S2, S3, and let us assume the PIs for this is given as 2/3, 2 by 9, 1 by 9, log of 1 by pi. If I assume that I am going to design a binary code, then is equal to 0.58, 2.17, 3.17. So, my Li which follows the inequality will be 1, 3, 4. So, I can design a code which is 0, 1, 0, 0, 1, 0, 1, 0. So, I have designed a code A which is based on this coding strategy. Now, if we calculate the entropy for this source, turns out to be Hs is equal to 1.22 bits per symbol, and if I calculate the length for this code is 1.78 bits per symbol. So, if you look at 1.78, it satisfies this inequality of HS this inequality is satisfied by this code A, but unfortunately this coding strategy does not give me a compact code, a code with the length, average length of the code to be as small as possible. So, if I take another code, in this case if I have another code say B, which is 0 1 0 1 1, which is again an instantaneous code, and you can calculate the length for this code, turns out to be 1.33 bits per symbol. So, what it means that this procedure does not guarantee a compact code. Now, this code B 1.33 is very close to 1.22. So, what it also implies that by going for an extension of this source, I may not be able to achieve much. So, what this example demonstrates is that using this coding strategy, it is not essential that we always get a compact code. We could get a compact code when n is very large, then when we consider nth extension of a source. Otherwise, we have seen in this example that if I follow another strategy, I could get average length of the code which is smaller than the strategy given by this inequality. Now, this strategy of coding is known as Shannon coding strategy or Shannon coding assignment for the lengths. Another question which arises is that whenever we design using this strategy based on some probability of symbols given here, but in reality if this probability is not correct, then what is the effect on the average length? So, let us answer this question. So, what we say is that we have a source S with source symbols given as S1, S2 up to SQ. The real probabilities of the symbols are P1, P2 up to PQ, but for some reason this is not available and the estimate of this probabilities are available. So, let us call those estimates given as Q1, Q2 up to QQ. So, as far as we are concerned, since this is known to us, we will be designing our code based on this information. So, when we do that, what it means that if we use Shannon code assignment, then my lengths for the code word for each source symbol will be decided by log of this is a symbol which we will use for finding out the first integer larger than this value. So, our designing of LIs will be based on Qi. Now, the true function or the true probabilities are given by this. So, the entropy of the source is pi log r pi. So, this is the real entropy of the source, and if we design our code properly, then we expect that the average length of our code should be as close as possible to HS. But since this is not known to us and we will be designing our code based on the lengths given by this probabilities, then the average length of the code which we will be getting in the practical case would be very much different from the entropy of the source. How much is the difference is in what is the difference in the entropy and the average length based on this is of interest to me, and this difference is given in the form of a theorem. The theorem says that the average code word length under real probability of real probabilities given by pi of the code assignment Li equal to log of 1 by Qi, this is what is available to me, satisfies the following relationship. Where by definition d of q is by definition given as pi log of pi qi, I is equal to 1 to q. So, this is what we want to prove. Let us look at the proof of it. The average length of the code which we will get is L is equal to pi is the real probability of occurrence of a source symbol, and the design length for this source symbol Si would be given by this quantity, because Qi's are available to us, and this quantity is less than pi I equal to 1 to q log of r 1 by Qi plus 1. This is equal to pi log of pi qr 1 by pi 1, and this is equal to summation of pi log r Pi Qi plus Pi log this by definition is equal to d of plus h r s plus 1. So, we have shown that L is less than h r s plus similarly, we can show the other side of the inequality, not very difficult to do that. So, we write L is equal to again Pi log of 1 by Qi, and this is greater than or equal to summation over I Pi log r 1 by Qi is equal to this can be shown as equal to so finally we get the result as h r s plus t of q where T of P Q is by definition given as Pi log Pi Qi so this is known as this is termed as relative entropy, or it is also known as Kullback-Leibler distance between two probability distributions. More appropriate would be to say to two probability density. So, the penalty which we pay for the wrong choice of the probability of the source symbol is in terms of the relative entropy. So, our average length is going to increase by this quantity. So, we have looked at the mathematical relationship between the average length of a code and the entropy of the source for which the code has been designed. We have also looked at some of the methods to synthesize an instantaneous code. Now, in the next class, we will have a look at different coding strategies which can be adopted in a practical scenario to obtain the average code word length to be as close as possible to the entropy of a source without going for the extension of a source.